When feeding a remote panel from a service, the feeder is required to be a 4-wire cable. The key reason for this requirement centers around the necessity of a dedicated neutral conductor for fault current return. In the event of a ground fault within the remote panel, the neutral conductor provides a low impedance path for the fault current to return to the source, which is the main service panel. This low impedance path is critical for ensuring that the overcurrent protective device, such as a circuit breaker or fuse, operates quickly and clears the fault. Without a dedicated neutral conductor, the fault current may have to find an alternative and potentially high impedance path back to the source. This could involve grounding electrodes, metallic conduits, or other conductive materials. High impedance paths limit the magnitude of the fault current, which can delay the operation of the overcurrent protective device. This delay can create a hazardous situation because the fault current can persist for a longer period, potentially causing overheating, arcing, and even fire. The National Electrical Code, or NEC, mandates the use of a 4-wire feeder to remote panels to ensure electrical safety and minimize the risk of electrical hazards. The code requirements are designed to protect people and property from the dangers of electrical faults. Firstly, the neutral conductor must be sized appropriately to handle the anticipated neutral load and fault current. The NEC provides specific guidelines for sizing neutral conductors based on the type and magnitude of the load served by the panel. Secondly, the neutral conductor must be properly connected to the neutral bus in both the service panel and the remote panel. These connections must be mechanically sound and electrically conductive to ensure a reliable return path for fault current. Thirdly, the grounding electrode system must be properly installed and connected to the grounding bus in the service panel. The grounding electrode system provides a connection to earth, which helps to stabilize the voltage and provide an additional path for fault current in the event of a ground fault. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes, that are buried in the earth and bonded together to form a low-impedance grounding system. For example, consider a scenario where a 200-amp panel is installed at the service entrance and a feeder is run to a subpanel in a detached garage. In this case, a 4-wire feeder consisting of 2 ungrounded conductors, a neutral conductor, and a grounding conductor is required. The ungrounded conductors carry the electrical power from the service panel to the subpanel. The neutral conductor provides a return path for the unbalanced current from the single-phase load served by the subpanel. The grounding conductor provides a path for fault current in the event of a ground fault. The neutral conductor is connected to the neutral bus in both the service panel and the subpanel. The grounding conductor is connected to the grounding bus in both the service panel and the subpanel. The grounding bus in the service panel is connected to the grounding electrode system. The purpose of the neutral conductor in a 4-wire feeder system is not solely for carrying unbalanced load current. While it does serve that purpose, its primary function in the context of electrical safety is to provide a low impedance path for fault current to return to the source in the event of a ground fault. Here is a more detailed explanation. Unbalanced load current. The neutral conductor carries the imbalance of current between the hot conductors in a single-phase or 3-phase system. For example, in a typical 120 volts or 240 volts single-phase circuit, if one hot leg is carrying 10 amps and the other is carrying 8 amps, the neutral conductor will carry the difference, which is 2 amps. Fault current return path. In the event of a ground fault, where a hot conductor comes into contact with a grounded surface such as a metal enclosure, the neutral conductor provides a low impedance path for the fault current to return to the source. This is crucial for quickly tripping the circuit breaker or blowing the fuse, thereby disconnecting the faulty circuit and preventing electrical shock or fire hazards. Grounding vs neutral. The grounding conductor, typically green or bare, is primarily for equipment grounding and provides a path for fault current to return to the source without energizing metal parts of equipment. The neutral conductor, typically white or grey, carries unbalanced load current under normal conditions and also serves as a fault current path. Separately derived systems. In separately derived systems such as generators or transformers, the neutral conductor is bonded to ground at the source. This creates a local neutral grounding point and ensures that fault current has a path back to the source. Impedance of neutral conductor. The impedance of the neutral conductor is crucial for effective fault current return. A low impedance neutral conductor ensures that the fault current is high enough to quickly trip the overcurrent protection device. If the neutral conductor has high impedance due to poor connections or undersizing, the fault current may be limited, delaying the tripping of the overcurrent device and increasing the risk of electrical hazards. Code requirements. The NEC specifies requirements for the sizing and installation of neutral conductors to ensure they can safely carry and balance load current and provide an effective fault current return path. These requirements include considerations for the type of load, the length of the circuit, and the ambient temperature. In summary, while the neutral conductor does carry and balance load current under normal conditions, its primary function in the context of electrical safety is to provide a low impedance path for fault current to return to the source in the event of a ground fault. This is essential for quickly tripping the overcurrent protection device and preventing electrical hazards. Here are some additional points to consider. Grounding electrode system. The grounding electrode system at the service entrance plays a crucial role in providing a reference to ground and stabilizing the voltage. It also provides an additional path for fault current to return to the source in the event of a ground fault. Separately derived systems. When dealing with separately derived systems such as generators or transformers, it is essential to establish a new neutral grounding point at the source of the system. This ensures that fault current has a dedicated path back to the source and that the overcurrent protective devices operate correctly. Bonding. Bonding refers to the intentional connection of all non-current carrying metal parts of the electrical system to the grounding conductor. This includes metal enclosures, conduits, and equipment housings. Bonding ensures that all metal parts are at the same electrical potential, which minimizes the risk of electrical shock in the event of a fault. Ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect ground faults and quickly interrupt the circuit. They are commonly used in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, or size are designed to detect arc faults, which are a common cause of electrical fires. They are required in many circuits throughout the home to provide additional protection against fire hazards. Regular inspections. It is important to have the electrical system inspected regularly by a qualified electrician to ensure that it is in good condition and that all components are functioning properly. Inspections can help to identify potential problems before they become serious hazards. Proper wiring techniques. Proper wiring techniques are essential for ensuring the safety and reliability of the electrical system. This includes using the correct wire size, making secure connections, and protecting wires from damage. It's important to understand the difference between grounding and bonding in electrical systems. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting non-current carrying metal parts of the electrical system together. The purpose of grounding is to provide a reference to ground and stabilize the voltage, while the purpose of bonding is to ensure that all metal parts are at the same electrical potential. The NEC specifies requirements for both grounding and bonding to ensure the safety and reliability of the electrical system. In addition to the NEC requirements, there may be local codes and regulations that apply to electrical installations. It is important to check with the local authorities to ensure that all electrical work is in compliance with the applicable codes. Working with electricity can be dangerous, and it is important to take precautions to protect yourself from electrical shock. Always turn off the power before working on electrical circuits, and use appropriate safety equipment, such as insulated gloves and tools. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. They have the knowledge, skills, and experience to perform electrical work safely and in compliance with the applicable codes. They can also help you to identify potential problems and recommend solutions to improve the safety and reliability of your electrical system. Remember, electrical safety is everyone's responsibility. By following the NEC requirements, using proper wiring techniques, and taking precautions to protect yourself from electrical shock, you can help to ensure the safety of yourself, your family, and your property. Here's a recap of the key points. A full wire feeder is required for remote panels to provide a dedicated neutral conductor for fault current return. The neutral conductor provides a low impedance path for fault current, which is essential for quickly tripping the overcurrent protective device. The NEC specifies requirements for the sizing and installation of neutral conductors to ensure they can safely carry and balance load current and provide an effective fault current return path. Grounding and bonding are also important aspects of electrical safety. Branding provides a reference to ground and stabilizes the voltage, while bonding ensures that all metal parts are at the same electrical potential. Electrical safety is everyone's responsibility, and it is important to take precautions to protect yourself from electrical shock.